we're going to look at systems with forces. A system is a combination of parts in which move together and one's actions reflect on another. We are going to start out with a pulley system. I'll show you what that looks like. Here we have two blocks of equal mass, 10 kilograms each. And I want you to think, will M1 move up or will M1 move down when I begin to run the simulation? Let's take a look at the free body diagrams. So there's gravity down and tension up. You should think which one of those forces is bigger. F equals ma, right? Look at M2. There's only one force. So you should be able to predict which way it will accelerate. So let's go ahead and look at some number values. Will this acceleration be 9.8? No, it won't be. Only 4.9. Well, that's because M1 is not free falling. It has to pull M2. So M2 is just kind of getting this extra mass along for the ride, right? Slowing everything down. So let's see how we can solve for that. And can M2 ever go backwards? These are things to start thinking about. Let's further explore the simulation that we just looked at. So when you come up across any sort of problem that involves forces, you're going to draw a free body diagram. So I'm going to take the two blocks from the picture and I'm going to separate them from the components of the picture, like the string in the table. From here, I'm going to add on my forces to each block. Now the freebie is gravity, mg. Mass times gravity, 10 times 9.8. Mass times gravity, 10 times 9.8. Now let's think about the other forces that act on our two objects. The 10 is on the table, so that will provide a normal force up. This normal force up is going to be equal to the downward force of gravity, 10 times 9.8, or 98 newtons. That's because this block is not accelerating up or down. It's sliding along the table, right and left. The rope is pulling this block. See? Rope. The rope is pulling this way. I don't know if you ever tried to push things with a rope, but it doesn't work. You pull things with a rope. So I have a rope pulling force to the right. We call a force from a rope tension, T. Now that exact same rope is strung over our massless pulley and onto this block here, with the tension now pulling up on block 2. So free body diagrams always have the forces that are acting on a specific object and the direction that they're acting on them. Once you've drawn a free body diagram, all you're going to do is you're going to take that information and you're going to convert it into math using Newton's second law. So let's write out Newton's second law for each one of these blocks. So what we're going to do is we're going to fill in sum of the forces, SUM equals MA for blue block, and sum of the forces equal the MA for the pink block. So let's look at the blue block. Let's look in the X direction because the block is only moving to the right. It's not moving up and down. What force do you see pulling to the right? You should see just tension pulls to the right. So this force expression is filled in with tension equals MA. We can take this one more step because you know the mass is 10. And that's all we can do with the blue block side. Let's go to the pink block. Things get a little sneakier in the pink block. The pink block is moving in the y direction, right? Like this, up or down. Wait a minute. Only down. So unless there's somebody who gives the system a push to start out with, there's no way that from rest this pink block will move up. So our pink block will accelerate down. So what we're going to do is we're going to think about what direction we want to call positive here. We might as well call this combo of directions positive, to the right and down, because that's the way our system is moving. Which means when you fill in some of the forces, you can think about winner minus loser, and always call A positive, because A will always be in the direction of the winning force. Now mg is winning. It's bigger than tension, because this system will be accelerating downward. mg is downward. So you're going to have winner minus loser equals ma. And we can fill in some numbers here. So 10 times 9.8 minus t equals 10a. Now these numbers 10, right? This 10 is from the blue block. Well, this 10 is from the pink block. They are different, and in a problem where they're not each 10, you'll need to be careful of that. So from here, what we can do is a little math technique and combine our two equations. So tension is 10A. So where we see tension over here, we can substitute in 10A. Okay, so now we'll have 10 times 9.8, and we'll add 10A to the other side, plus 10A. So on the right side, we'll now have 20A. Now we can divide by 20 on each side. So A will equal 10 times 9.8, 98, divided by 20. The acceleration for the system is 4.9 meters per second squared, which is what we saw when we ran the simulation. Now I want you to think about, what is this value of t? Is t equal to 98? Is t less than 98? Or is t greater than 98? If this 10 is accelerating downward, that means the downward force must be larger than the upward force. 98 must be larger than tension, right here. Do you want to know what tension is? Well, you happen to have an equation for it. T equals 10A. So just go right ahead and say, oh, T equals 10A. And you discover the tension is 49 newtons, which is indeed less than 98, letting the system accelerate downward/rightward. Connecting this back with the concept of systems, what is our system? Our system is the entire pulley system, which is why we will connect the objects together, building one full expression for their motion. So here we have a system composed of two parts. 1, 2. So we have two individual sections of our system, and they are connected by the tension T. So the number of objects that you choose inside your system is the number of free body diagrams that you need, and is the minimum number of Newton's second law expressions that you're going to have. Okay, so checking out a way to take advantage of systems. So in this system, pulley system, singular system, we're going to analyze two objects. Later, we're going to come back and treat the system as one single object so that you can take advantage. So we're going to look at each block separately. M1, we will have tension pulling to the right. We will have M1G down due to gravity and a normal force up. And these two forces will be equal and opposite. On M2G, you are also going to have gravity pulling down and tension pulling up. We have two separate free body diagrams that we've made, and we're going to make two corresponding Newton's laws from them. So we're going to need one Newton's law expression, at least, to fill in this block. So the tension will pull this block to the right. Now, if we look at M2, we should really explore the scale in which we drew these vectors. Which one of these forces is going to be bigger? Well, which way will the system be accelerating? Imagine it. You realize that M2 must be accelerating downward. If released from rest, M2 would move down. M2 must be winning, must be larger than tension. Winning. Okay, so when we go ahead and fill in the Newton's second law expression for M2, we'll have winner minus loser equals MA, and we'll call the acceleration positive. That's this way, A. So the winner is M2G, the loser is tension. When you fill in this mass, it's about the system here on the right. So we'll use M2 times A. There are numbers to this problem, so let's go back and we'll fill in some numbers. So T equals M1A. M2 times G minus T equals M2A. Now there are two equations with two unknowns. These unknowns will be the same quantities, T in this picture is the same as the T in this picture. These T's are the same T's because it's the same rope. Now, given that you're attached with a rope, that means these accelerations are the same as well, because the amount that M2 moves down is the same as the amount that M1 moves right. And they're stuck together, so the speed of M2 is the same as the speed of M1. And therefore, the accelerations of each one are also the same. So let's go ahead and combine these two equations. So you may use a technique called substitution, or you may use a technique called, I guess, linear combination or something like that. So you can add these two expressions together. It's going to look just the same as substitution. So here we have 4 times 9.8 minus t, and t will cancel. 4a plus 2a is 6a. So you'll have 39.2 over 6, which is our a. Okay, I told you I'd tell you to take advantage of the system. I'm not talking like the healthcare system. I'm talking like a physics system. So redefine this whole system as just that, one system. So take the 2 and the 4 and look at them together as one big blob. So when we draw our forces on the 2 and the 4, we're going to be considering them to be one big blob, rope included. So this whole thing is going to be our system. Our system will mean that when we draw our forces are external to our system, outside of our system. So the rope is not included, the rope is inside. Here we're going to have the mg, the 4 times 9.8, pulling down. And on the other side, oh, we have nothing. Well, we do have things. Actually, we have this and this. But they don't affect the right/downward motion of our problem. So we're not actually going to include them. When you take advantage and you draw your system as one large lump, and you write out sum of the forces equals ma, it's only the external forces that will affect the direction of acceleration. So this is in the direction of A. And there's no other force in the direction of A, because our rope is inside of our system. Remember, forces are always external. What's the mass of this whole giant blob system, the 2 and the 4? That total mass is 6. So for M, you'd put in 6 and A. And notice that simplifies us right down to the same spot that we obtained earlier. 39.2 is 6A. So this is how you can take an advantage of a system. You can draw the system larger and include the rope inside your system and make the mass bigger. You're welcome. Learning how to exploit the system.